Welcome to this IAS lecture. I'm Professor Mert from ECE, and it's my great pleasure to have Jamal Deen present this lecture. So Jamal is extremely accomplished and has won many awards and prestigious achievements in his career so far. And rather than read out the list, I think the list of all his achievements would actually last longer than his seminar. So I just highlight one thing. He's actually a fellow of 8 different organizations and societies, I believe. And in our department, we have 20 IEEE fellows, but then Jamal was 8 in one package, so it's quite an impressive achievement. So Jamal's research area is microelectronics, nanoelectronics, and I think optoelectronics. And one of the reasons he's visiting us is because we have an interdisciplinary project on water quality, water pipe infrastructures, and so on. And so Jamal was helping Amin on sensors for that project, and then I'm also involved helping with the communication side of that, so it's a great pleasure to have Jamal here. So without further waffling, let me hand it over to Jamal.
Okay, so good afternoon, everyone. It's always difficult to give a talk on Friday afternoon because everybody's looking forward to the weekends. But in any case, I was asked to give a talk on Friday, so I'll try my best. Today what I want to talk to you is how we can actually extend how we see. So this is one of the 5 senses that us as humans have. And I'm going to divide the talk into 2 parts. The first part is looking way into the future using new kinds of image sensors that are called quantum dot-based devices. And I will concentrate on those devices operating mostly in the medium wave infrared. And I'll explain to you why we're interested in the medium wave infrared. And the second part of the talk is looking at more near-term applications using mainstream silicon semiconductor technology. This is using silicon to actually build high-performance silicon photodetectors and silicon imaging systems. So first on quantum dots and quantum dots infrared photodetectors. So the reason we're interested in this is that the infrared offers many opportunities when we use imaging systems that are designed to operate in the infrared regime for looking at physical phenomena. One of the things we can do is we can apply such imagers for thermal imaging. And in the bottom right, you can see a picture of a fox in which you can see the high temperature parts and the low temperature parts that go from around just in the low 20s to the mid 30 degrees Celsius. Such an imaging system is made using this 2-dimensional focal plane arrays. The main applications for such imagers are in thermal imaging, but originally the principal applications were in the military area, and these days there's a lot of work in the biomedical and environmental area. We can also use it, as I just mentioned, in the environmental area. We can use it for thermal remote sensing. So here's an example of where we can actually use it to monitor heat distribution and the heat efficiency of insulations that we have in buildings. We can also use it to monitor forest fires. And this is an infrared imager that is actually out in one of the space imaging system. It's ALI system, so this is part of a satellite. And it's imaging using 10 imagers that are operating from 0.48, so from the visible regime, to the mid-infrared, so 2.35. And this shows a fire that took place in the Glacier National Park, that is the southwest part of Montana, near to Idaho, and also the northern part of Alberta. So you can see the fire that is shown here. We can also use these systems to actually monitor environmental pollutants. And this is an example of looking at ozone and looking at carbon monoxide in the North American continent. So going from the south part of North America to the north part of North America, and you can see that there's a depletion of the ozone that is shown here as compared to the southern part of North America. So if we look at the infrared regime from around 2 microns to 2-point-something microns, you can see there's a lot of windows. These are the absorption windows. So here we're looking at transmission versus wavelength. And you can see absorption windows for carbon dioxide, for water, etc. So we can actually exploit these absorption windows to make a map of what's happening on the surface of the Earth and above the surface of the Earth several kilometers. For example, looking at cloud distributions, etc. We can also use it to see things that we normally cannot see using visible light. So this is an example of a container in which we've taken an image using visible light, and we cannot see the identification mark. However, if we extend the range of wavelength, and this is using indium antimonide camera, from 1.5 micron to 2.5 micron, we can clearly see the identification mark. So these types of images really allow us to extend our ability to see as humans. And very often, we can see things that we cannot see using visible light which our eyes are most sensitive to. Now, these imagers have traditionally been made using technology that is based on 2,6 semiconductors. An example of the 2,6 semiconductors would be mercury, cadmium, telluride. But these days, most of the semiconductors that are made using these exotic materials that are somewhat toxic, like mercury, are being replaced by compound semiconductors from group 3 and group 5. And this is an example of such new type of semiconductor infrared detectors that exploits two types of phenomena. We can have a phenomena where we have charges that are trapped in a bound state in one of the band edges of the semiconductor, and we can, by shining light, we can give those charges enough energy to remove them from a bound state to the continuum states. And the wavelength of response would be dependent on this energy difference. And this energy difference would be exploited to image in different wavelength regime. So this is a bound continuum quantum well infrared photodetector. We can also exploit bound to bound. So here we have charges that are trapped at one bound level within one of the band edges, and it can get excited at a different localized level, in this case in a quantum well with light of an appropriate wavelength. So we can have a bound to bound transition. And the range of wavelength over which these 3-5 semiconductors operate over exploit both phenomena, both bound to bound and bound to continuum transitions. And by exploiting these phenomena, we can have a very wide wavelength range of response, from visible going all the way to medium wave infrared and even to long wavelength infrared for many applications, again mostly in the environmental area and in the biomedical area. Now, I'm particularly interested in quantum dot infrared photodetectors, which is abbreviated Qtips. So these are little dots that exhibit very nice quantum phenomena because they're small size. They're typically made using 3-5 semiconductors, and they're typically made using a common technique that is called VLS. So this is for vapor, liquid, solid technique. Essentially, you seed the semiconductor with a small seed metal. Gold would be an example. And then using the VLS technique, you can actually grow these nanostructures. And you can grow it to various heights and various dimensions depending on the growth conditions for such nanostructures. So they're typically made using 3-5 semiconductors grown in an epitaxial system. An examples of epitaxial system would be molecular beam epitaxy or MOCVD, metal organic chemical vapor deposition. These are the two common ones. We can have uniform surface growth, so this is a well-developed technology that allows us to grow repeatable and reproducible Qtips. And one important aspect is that because they are small structures, we can have 3D, three-dimensional carrier confinement in these quantum dot devices. So this is really very important. It has several other important advantages. This one is particularly important, so intrinsic sensitivity to normal incidence. And this is a big advantage compared to its predecessor, and its predecessor was not QDIP, but QWIP, QWIP. This stands for Quantum Well Infrared Photodetectors. So we've made a transition from the older technology that is a quantum well-based technology to the more modern, more current technology that is a quantum dot-based technology. And this offers lots of attractive features. So because of this intrinsic sensitivity to normal incidence, the optical configuration for coupling the light into such photodetectors is relatively straightforward. It has long-lived excited states, which are important for improving its response, leading to higher responsivity. It has reduced electron-phonon scattering, so this is important because it allows us to lower the noise and improve the sensitivity and dynamic range of the device. It has low dark current, and it has relatively high operating temperature all the way to room temperature and beyond, as compared to quantum well infrared photodetectors that were typically operated in cool configuration. This means below room temperature. Now, First, I'll explain to you why we're interested in modeling. And modeling has been one of the big advances in the semiconductor field. So if you go back in the history of semiconductors in the 60s and 70s, there were no standard models that people could use to design devices and use those devices to design circuits and systems and predict the performance of such circuits and systems so that when they actually fabricate the circuit and system, the prediction would be closely matching the experimental results. With the advent of sophisticated models, people were able to use foundry services and make really sophisticated electronic designs that work correctly at first fabrication attempt. So modeling plays a really important role in the evolution of the electronic industry, and it's been one of the bottlenecks in the compound semiconductor field because there are no standard models that people can use to design into a fabrication house as we have in silicon-based semiconductor devices and also photonic devices. So if you look at this table, it shows many interesting things, but I just want to draw your attention to two aspects, the economic aspects. So because models are very sophisticated, models are properly calibrated, models capture all the important physical phenomena, geometrical phenomena, operating phenomena, environmental phenomena of these devices that are used in circuits and systems, again, we can have success at first fabrication attempt, and we can do it relatively quickly. So because of the models that are available to most designers, we can have 40% savings in the technology development time. This means that if we are, for example, developing a new product, we can do it much faster because it allows us to refine, optimize the performance of such systems so that we can have, again, success at first fabrication attempt. And there's also 40% savings in the overall technology development costs. And these are lower bounds. What this means is in reality, because the models are sophisticated, the models are accurate, and the models capture most, or if not all, of the important phenomena for circuits and systems we're designing, we can have these huge savings. And again, this is something that is lacking in the compound semiconductor field. So we spent a lot of time trying to develop models that can capture the performance characteristics of these new type of quantum devices. Such models are far more complicated than the models that are used in silicon semiconductor devices because here we're dealing with really small structures. I told you they're quantum dots that have 3D carrier confinement. And we have to couple the quantum mechanical formulation with the standard semiconductor physics so we can start predicting the performance of the device. And then if we want to sweep temperature, we want to sweep up operating conditions such as voltage or current biasing conditions, or we want to sweep wavelength, or we want to sweep incident optical power, we have to include those in the formulation. So the formulation I've been using to predict the performance of these devices is a relatively new formulation that is being applied in the semiconductor field. This is a formulation that is based on the Nonequilibrium Green's function. So the Green's function was a very powerful technique that has been widely used in the electromagnetics area. And it's only in the last couple of decades has its use found its way to predict the performance of semiconductor devices. So what do we need to do? We need to capture the important physics that describe the operation and performance of the device that would allow us to develop efficient models, and then we have to calibrate these models using benchmark devices and circuits so that when we actually design devices and circuits, they will behave as we predict. So we compare to experimental results, and once the models are calibrated, then we can start looking at different kinds of optimization depending on the performance we're after. So we can look at optimization, but optimization must take into account the full technology constraints. This means that you cannot design a device that you have no chance of fabricating. So you have to look at what are your technological constraints that are dictated by the fabrication equipment you're using, operating conditions, etc. And using those technological constraints, you can actually design device with tailor-made or custom-made performance characteristics. So you can look at new structures, you can look at improved electrical performance, and you can also look at improved optical performance. And in this way, we can have optimized device design, and we can also have new device design. And this has several important advantages. So we save time when we actually coming up with a new idea and we want to prove that the new idea is feasible, or we're designing a circuit. Tremendous cost savings. We can put it in the device simulator, and we can use that device simulator in standard circuits and system simulator to start developing bigger systems. So as I told you before, the formulation we're using is non-equilibrium Green's function, and this allows us to calculate a retarded and an advanced Green function. And with this retarded and advanced Green's function, we can look at the electron dynamics and the electron states within these localized states that are present in these quantum structures built using 3-5 semiconductor devices. We can look at the lesser and greater Green's function. This allows us to look at the state occupation levels and correlations. We can look at the retarded and advanced self-energies. This allows us to look at the shifts in energy levels, to look at states decay rates. And it also allows us to look at interactions and to take into account practical considerations. Examples of practical considerations would be electron-electron scattering, electron-phonon scattering, and electron-photon scattering. So we can include all physical phenomena that are important in the operation of such devices. We can also look at the in-scattering rates and the out-scattering rates. And with this, together with the appropriate semiconductor formulation, we can predict all the electrical and electro-optical performance characteristics of such devices. So in the first part of the talk, I'll show you how we can use such a formulation to predict the performance of the device, to calibrate the model, and to actually start optimizing device structures for specific applications. So this is an example of a quantum dot infrared photodetector. The solutions we're developing is quasi-compact. It's quasi-compact in the sense that part involves analytic formulation and part involves numerical solution. So this is the part that involves numerical solution. So you have to develop an appropriate grid for the important aspects of the device. This is a scanning electron microscope of a quantum dot infrared photodetector. So here you can see an indium arsenide quantum dot. This is a physical representation of the structure with a quantum dot that is shown there. You have your Green's formulation. This is a calculation that shows the indium arsenide quantum dot with a wetting layer and the barriers that are shown on both sides. So using the formulation I explained to you, together with the appropriate physical structure of the device and the appropriate boundary conditions, we can start computing the performance characteristics of the device and then optimize the performance of the device. So this is an example of the responsivity as a function of wavelength. And in the first instance, what we're interested in doing is looking at where these peaks come from. What is physically responsible for such peaks in the quantum dot structure. So this is quantum dot in a well. So in such a case, we can actually calculate the density of states as a function of energy. We can look at the localized states within the quantum well and in the wetting layer. So here we have 3 states, E0, E1, and E2. And if you look at these states, we can see that the transition from from E0 to E2 is responsible for this first peak, and this corresponds to this transition here. This second peak, the around 10 microns, could either be from E0 to E1 or E1 to E2. And the third peak that is shown here at around 23 microns is the one that is responsible from here to the continuum. So from E2 to the continuum. So in this way, we can actually look at the structure of the device. We can determine all the localized energy states. And then we can look at transitions between these localized states or from a localized state to the continuum that gives rise to the specific features that we observe in the responsivity. Responsivity is an important characteristic because it tells you that if you have a photodetector and you shine a certain amount of light, how much current will you get? The higher the current you get, the better is the overall optical response of such a device. So having the responsivity and being able to relate it to physically what's happening within the device and also the structure of the device would allow you the flexibility and the capability to optimize the performance. So for example, you can try to push this responsivity to higher and higher value, which means that your device would be more sensitive to less light. This is an example of a computation of the dark current density as a function of biasing condition using the formulation. So again, you can see that the model is relatively well calibrated. So the symbols are the model, the solid lines are the experiments, and you see we can predict the experimental results from 80 degrees Kelvin out to 300 degrees Kelvin. So once you have such a model, you can benchmark it again against other performance characteristics. So here again, we're looking at responsivity as a function of wavelength. For 2 different devices. Now these are more sophisticated devices. So this one here is a resonant tunneling quantum dot infrared photodetector. So what it allows us to have is resonant tunneling between one side of the device and another side of the device, and in this way we can improve the performance characteristics. The second type of quantum dot infrared photodetector is one that is built using superlattices. So this is called a superlattice quantum dot infrared photodetector, and for both of these we can predict reasonably well what are the performance characteristics based on the structure and the materials characteristics of the device. We can also do some optimization. So in this case, I just show you a few examples. So here we're looking at the shape effect. So in this case, what we do is we change the height to diameter, but we keep the same number of quantum dots and the same doping density within the structure. And in this way, we can see, for example, as we increase the height, so from 3 to 4 to 5, we have a better response. And in this case, if we increase the height, so from 3 to 4 to 5, and we keep the dot diameter the same, so 18 nanometers, we can see that there's a decrease in the performance characteristic. In this case, there's an increase because we're increasing the diameter and the height to keep the density the same and the same number of quantum dots. So these are related to actually how we fabricate the device. So we can start fine-tuning the fabrication parameters so that we can improve the performance by playing with the height, by playing with the diameter, and by playing with the doping concentration. And in this way, we can design a device that has tailor-made characteristics. We can also look at the number of quantum dot layers. So in this case, we have 10 quantum dot layers, 15 quantum dot layers, and see how it affects the dark current, which would affect the sensitivity. We can look at the barrier, so changing the barrier height from 30 nanometers to 50 nanometers and how it impacts the dark current. So the wider the barrier height, the less the dark current. We can also look at the relative doping densities of the quantum dots and how this affects the performance. So we can look at many different fabrication-related knobs that we can tune to improve the performance characteristics of the device. We can also look at what happens if we apply strain to the device. So strain is a common technique that is used to actually tweak the wavelength response if we want to extend it between the physical sort of phenomena that I showed you between bound to bound or bound to continuum transitions. This is an example of where we changed the number of quantum dot monolayers from 2.2 to 3.0. So you can see the density is changing, and in this way we can change the response of the device. So using these models that are computationally very intensive, but robust enough, robust in the sense that it's accurately calibrated to experimental conditions, we can do many things. And some of those things I already showed you. And as I mentioned earlier, this is one of the limitations in the rapid deployment and application of compound semiconductors. There are no commercially available models that people can use to design into fabrication house similar to what we have for the silicon semiconductor field. And this is a really big advantage of silicon electronics and silicon photonics. So that's the first part of the talk. And the second part of the talk, I'll show you how we can use near-term semiconductor devices. So these are devices that are built using silicon semiconductors to create new types of photodetectors and imagers. So first I'll explain to you how we can create an ultra-high-speed imager. This is one that is operating at phenomenal speeds using a standard structure. This standard structure, which is the same structure that you have in your camera or the camera that is in my computer, it's built using active pixel sensors. So this is a 3-transistor plus a photodetector structure that allows us to actually address each individual pixel in a 2-dimensional pixel array. And your pixel array could be 18 megabytes, 42 megabytes, or 6 megabytes. Now, one of the limitations in improving the speed of the device is that the speed of the imager is that if we have a big imager, we have to take the information from that imager and from the imager itself and put it, for example, in a computer or some other signal processing or image processing tool so that we could actually look at the image eventually. So if you have to do that, the bigger the size of the imager, the slower would be the speed at which you can operate it. Because you capture an image and then you have to shuffle this image out of the imager so that you could do different things to it. For example, you can display it, you can process it, you can manipulate it, etc. So to improve the speed of the imager for relatively large 2D array, what we can do is we can separate out the process into two parts. one part that is involved in capturing and a second part that is involved in transferring the captured image externally to the imager. So to do this, one of the ways in which you can get around this speed limitation is to locally put next to the imager or the imaging element small memories that allow you to locally store the image information that is captured at a very high rate and then transferred out of the imager at a slow rate. So in this case, we're separating the image acquisition process from the image transmission or transferring out of the imager process. So we have a two-step process. We capture the image at a very, very fast rate, and then we transfer it out at a slower rate when we don't need such high speeds. So this is an example of this 3-transistor structure. Here you can see the imager. It's a photodiode with some intelligence. This is why it's called an active pixel sensor, because we can actively address and we can manipulate the image that we see. And in this case, we only have one memory element. So what I would like to do is, I would like to capture the image really very fast and then transfer it out at a slow rate. So what we've done is, we've added locally 8 memory cells. So this allows us to get 8 frames very fast. Really very, very fast. And I'll show you how fast we can do it. And then we can transfer it again out at a much slower rate. Of course, there's always a compromise when you make some advance in one area. The compromise that we're making in this case is that the size of the imaging element, so this photodetector actually shrinks relative to the size of the pixel to accommodate all the extra electronics you're going to add to improve the speed of image acquisition. So we change from a higher fill factor, so fill factor is just a measure of the area of the photodetector to the size of the pixel, to a relatively modest fill factor of around 10%. And this is the design that was done in 130 nanometers a few years ago. So if you look in the literature, if you have digital readout architectures, typically you're limited to several tens of kiloframes per second. And if you have analog readout architectures, you're limited to a couple hundred megaframes per second. Using this new procedure, we are able to push the speed to 1.25 billion frames per second. This means that you can capture an image with a sub-nanosecond response time. And I'll explain to you why we want to do such high-rate image capture. It's very important for clinical applications and for biomedical applications, and also for some environmental applications. So again, in this case, we can push it from a few hundred megaframes per second to more than 1.25 billion frames per second, which means that you can capture time transients that are sub-nanosecond. This is the imager. These are some of the results that we had. So we can capture 8 frames at 1.25 billion frames per second, and then we can read it out at a much slower rate. In this case, we can read it out at 20,000 frames per second. So when we don't need to capture so fast. Right, this is the imager that we designed. This is the real imager array that was used in those experiments that were shown. Now, here I showed you how we can actually improve the speed of image capture. But there are a few other things that we need to look at. Very often, you're dealing with situations that are called photon-starved situation. This means that you're starved of photons. You don't have a lot of photons. So if you don't have a lot of photons, you have to design very, very sensitive photodetectors that are sensitive enough so that when a couple of photons, even down to 1 photon comes in, it will say, yes, I've detected a photon. So how can we do that? The second thing that we may need is, in some applications, we may actually want to separate out the wavelength components of the imaging situation we're looking at. So we may be looking at broadband radiation, but we want to know what is the response at individual parts of that broadband radiation. So we need to look at 2 other things. One is, how can we push the sensitivity down to very, very low values? Because in many environmental applications and biomedical applications, we're operating in this photon-starved regime. And the second thing we may want to do is we may want to look at the spectral characteristics of the scene we're looking at, the radiation we're trying to capture. So I will show you how we can actually address both. So I showed you about speed, and now I'll show you how we can push the sensitivity, and then how we can push the response over a range of wavelengths. And ideally, what we would like is for such systems to be really tiny. So I'm going to explain to you how we can exploit some of these ideas to create what we call a micro Raman spectrometer. So this is a spectrometer that is really very, very tiny. Now, if you recall from your high school physics, the spectral resolution of a spectrometer is related to the optical path lengths. And the high performance optical spectrometer are typically benchtop type instruments. So if you want to make this really tiny, it means that your optical path will be smaller, and if your optical path length is smaller, then you will suffer in terms of wavelength selectivity. You may not be able to differentiate one wavelength from a nearby wavelength. But there are some tricks that you can do. So there are two tricks you can do. One is you can use what is called optical folding techniques to actually increase the path length to be equivalent to what you would have for a much bigger system. And the second trick you can do is to try to combine the functionality of different optical components so that one optical component does the work of 2 or 3 or 4 individual optical components in the bigger system. So again, try to combine the functionality of individual optical components into more cleverly designed optical components and do optical folding. And in this way, you can transform a benchtop type instrument into a small instrument that could be useful for biomedical or clinical applications. Because in those applications, size is really very important. So these are some of the people who are working with me in this project. So first I'll explain to you how we can address sensitivity and how we can address the optical folding. And I'm going to do it using a system we're developing. It's a Raman system. So in a Raman system, you excite some sample with light of a specific wavelength, and you can either have an upshifted in wavelength response or a downshifted wavelength in response, depending on whether you're looking at Stokes Raman scattering or anti-Stokes Raman scattering. So the Stokes Raman scattering is shown in red, and the anti-Stokes is shown in blue, and the green transitions are the common Rayleigh scattering. Now in such systems, what we would be doing is we would be exciting the sample with light of a certain intensity, and most systems would give back two responses. One response is this tiny one that is shown in green. This is the Raman response, right? This tiny one that is shown in green. And the larger response is the fluorescence response. And most biological systems have a natural fluorescence response. This is called autofluorescence or biofluorescence. So what we're interested in doing is looking at a Raman response, but the Raman response is typically swamped by the large fluorescence response. When I say swamped, I'll give you some specific information. So for example, if the input is 1 million photons, it's not uncommon for the Raman signature to be just one photon or a few photons. So again, 1 million photons is coming in, and you can get one or a few photons back. This is the Raman signature. The fluorescence signature could be several tens of thousands of photons. So again, 1 million, several tens of thousands versus one or a few. So how can you detect such a tiny signal that is swamped by a much larger signal? So look at its characteristics very carefully. So what we want to do is we want to detect this tiny signal that is a Raman signal that is swamped by this much larger signal. So I'll come back and I'll explain to you how we can do this. So some possible solutions are to use devices that are really sensitive to single photons. So these are called single photon avalanche diodes. And if you look at this characteristic very carefully, what you can see is that the Raman response is almost coincident with the incident signal, but the fluorescent response has some time delay. So even though it's much weaker than the fluorescent response, we can exploit this differentiation in the time response characteristics to actually extract out this extremely weak signal that is swamped by the significantly larger signals. The circuit that you can design is a circuit that would be operating in a time-gated mode. What do we mean by time-gated mode? We would have a very smart photodetector, and it would be like a gate that is open for a very short period of time and allow these early photons or Raman photons to be detected, and immediately after it's detected these Raman photon, the gate will be closed. And it will no longer be in a detection mode, so that this much larger fluorescent signal would play no role in terms of the response characteristic of the device. It's like you have fast runners and slow runners, and you only want the fast runners to pass a certain point. So you put a gate, and you open the gate, and when the fast runners have passed, you closed it so the slow runners cannot go by. So this is the basic idea here. And what we're going to do is we're going to build such a system using mainstream semiconductor technology. So again, silicon semiconductor technology, so that the cost would be very low. So this is going to address our ability to detect an extremely weak signal that is swamped or overwhelmed by a much larger signal, but has this small differentiation in their time response characteristics. And again, we're going to be building it using standard CMOS technology. Now, what is the competitor to the detection device I'm proposing? The competitor to the detection device I'm proposing is this one here. This is a relatively old device. It's called a photomultiplier tube. It's like your standard vacuum tubes that you had in your old radios or your old TV. It's actually as big as a vacuum tube. And it has several disadvantages, but many advantages. So first, the advantages. It's very fast. It can have sub-nanosecond response. And it's very sensitive. It can be sensitive down to single photons. So this is called a photomultiplier tube, or PMT. The disadvantages, it's very big and bulky. It's very difficult to put it in a two-dimensional array format, so it can operate most of the time as a single detector and not an array of detector. And it requires very high voltages in the order of thousands of volts, 1,000 or 2,000 or even higher volts. So very high voltage, very big size, not amenable to integration in the two-dimensional format, so that we cannot do two-dimensional imaging, and very costly. So what I'm going to do is I'm going to design a device using standard mainstream technology that is going to compete with this. So how do we do that? So this is, so let's just go back here. So this is a standard current voltage characteristic of a diode. So you can see one diode here, one diode here, one diode here. This is the one we're interested in. And typically when we're operating the diode as a photodetector, well, the diode typically has response characteristics in three quadrants. The first quadrant, the third quadrant, and the fourth quadrant. So the first quadrant is used in things like rectifiers. So it takes an AC signal and it rectifies it and gives you a DC voltage. The third quadrant is typically used in the photodetection mode. So this is when it's sensitive to light. So when light comes in, this curve actually shifts down. And the amount by which it shifts down is proportional to the light that is incident on it. And in this fourth quadrant here, typically we use it as a solar cell. So today I'm going to concentrate on the third quadrant. And we can operate it either in this part here, or we can operate it in this part here. This part here, it's actually breaking down. So how do we do it? So let's just go back. So I'm going to take this curve, and in the next slide, I'm going to plot minus current versus minus voltage, so everything will appear in the first quadrant. So that's this part here. So minus current versus minus voltage. So you have the diode in the reverse characteristic. This is in the dark. Then it starts increasing, and then I'm operating it now in the breakdown mode. This part here is typically referred to as the linear mode of operation. This means that when you're in this mode, the change in current is linearly related to the incident light. But what I'm going to do is I'm going to operate it beyond the breakdown mode. And this line, this red line, is drawn with some slope. In reality, it's much steeper. So this line will be going up much, much faster. This mode here is the breakdown mode. The device has a breakdown voltage that is related to the physical characteristics of the device and the doping concentration. So I'm going to be operating it beyond the breakdown mode. Now, for example, let's pick a number. Let's say this is 10 volts, so 0 to 10 volt. I may be operating it at 12 volts. So from 10 to 12 volts, this current would be really very, very high. So again, at 12 volts, the current would be high. In fact, it would be so high that the current multiplied by the resistance of the device would generate so much heat that that heat would burn the device up. So again, this is the breakdown voltage, 10 volt. I'm going to operate it at many volts beyond the breakdown voltage, where in principle, the current will be really large, and the heat that is generated by this really large current could destroy the device. So how do I operate it in such a mode? So I'll explain that to you. So first, we arm the device. So we bias it at the voltage that is beyond the breakdown voltage. And then when an incident photon comes in, because the voltage is very high, this means the electric field is very high. So this very high electric field, when an incident photon comes in that generates an electron-hole pair, will cause an avalanche phenomena to occur. And this avalanche phenomena will generate billions of electron hole pairs, could be trillions, could be thousands of trillions, right? The current could be really huge. So what we need to do is, once we sense a photon has come in and has generated an electron hole pair, we have to have some mechanism to actually turn this device off by switching the voltage from a voltage beyond breakdown to below breakdown, which means that the gain would be reduced. So again, the gain is very, very high. It could be billions, it could be trillions, it could be thousands of trillions, but once it senses one photon and it's only responsive to the first photon, it will shut itself down. So it will shut itself down, so we quench it, so we stop it, and once we stop it by biasing it at a voltage beyond the breakdown voltage, then we will stop this avalanche process from continuing, and in this way the current will be clipped, or it will be clamped to some finite value. We don't have this very high heat that is generated to actually destroy the device. So we quench it, and then we reset it, and we wait for the next photon to come in. And if we want it to operate very fast, then we have to have the capability to actually do this arming and quenching very quickly, so that we could be sensitive to one photon, down to one photon, so it could compete with a photomultiplier tube. And it could also operate at very fast speeds, so we can start looking at biological phenomena that is important for medical diagnostics. Right? So we can do this using what is called a gated operation. So we allow the device to be on beyond breakdown for some period of time, and this should be synchronized to the light pulse that is illuminating the sample, and then you shut it off. Now, in this mode, several things happen. So first, the responsivity can be down to the single photon level. So this is why it's called a single photon avalanche diode. We have to be careful about dark current, and the concept of excess noise, or noise in this case, does not apply because it's sensitive down to one photon. However, we have to be careful about other noise mechanisms. And one of the other noise mechanisms is that when it's biased beyond the breakdown voltage, if I have some other means to generate an electron hole pair that is not linked to an incident photon, then the device will be triggered, and I have to reset it. One mechanism for generating these other types of electrons and hole pairs is through thermal generation. So once your device is operating at a finite temperature, from statistical physics, there's a finite probability that there will be electron hole pairs generated, and we have to suppress such generation. You can do several things to get around that. Today there's no time to explain this. The other thing you need to do is you need to pick your threshold very carefully, right? So for example, if we pick a threshold here, we would detect the first photon, but because our threshold is too high, we would miss the second photon, and we would detect a third event, but this event is not related to an incident photon, but is related to a dark count, this electron hole pair that is generated from thermal means. Now, these devices, as I told you, are sensitive down to single photons. So how can we also improve the speed so we can make it fast and very sensitive? And then the other thing I need to explain to you is about wavelength selectivity. So the way we make it fast is we design a circuit that will sense when this device starts breaking down, right? And once it starts breaking down, it will quench it, and then it will reset it and wait for the next photon to come in. In this example, so this is a real experimental result, you see that we can do this in around 20 nanoseconds. But we want things to be in the order of 1 nanosecond or sub 1 nanosecond. So by redesigning this circuit and doing it in a more advanced CMOS technology, in this case 130 nanometer technology, I'm able to actually decrease this time to around 0.5 nanoseconds. What this means is now I have a single photon detector that is capable of response times that are sub-nanoseconds. This means I could start looking at biological events that are in the order of nanoseconds, or even below 1 nanosecond. And I could be operating it in situations that are photon-starved situations, that are typical of biomedical applications. So this device was used in this micro Raman spectrometer, operating in a time-gated mode. And we designed one of those optical components that combine the functionality of several optical components, so we can actually do the wavelength separation. So rather than have mirrors and lenses and a planar grating, what we've designed is a concave grating. So we combine, again, the optical functionality of many components. And with this with this concave grating, right, so curved grating, we can do focusing and we can do wavelength separation at the same time. So this allows us to actually miniaturize such a Raman system, and we can use this for probing biological molecules, or we can use it for probing chemical species that could be environmental contaminants that are present, for example, in water. Now, how do we actually make the response very fast? So one of the things we can do is we can turn on the device for a certain period of time, right? So this is the device that is on for a certain period of time. In this case, we fixed it at 3.5 nanoseconds, but I can actually make the response much better than 3.5 nanoseconds. How does the device respond? It responds when it receives an incident photon. When does it receive an incident photon? When the sample is illuminated by the light source. This is the laser excitation. So by moving where is this laser excitation occurring relative to the end of the on time or the gate of the S path, so by moving from this point here relative to the edge here, I can actually change the response time. So in this case, I have a certain detection window. If I move this closer to the end of the on gate, the detection window will be shorter, which means the response time will be shorter. So it will be a faster device. If I move it to the left, it will be a slower device. So by moving this laser excitation relative to the end, right? So if I move it to this point here, I have a faster response time. And in this way, I can actually play with the response characteristics of my imaging system. And since it's built using mainstream semiconductor technology, I can start thinking of building a linear array or a two-dimensional array to look at two-dimensional mapping, depending on the application I have in mind. Right? So this is an example of one of those chips. This is the packet chip. This is shown here. This is the chip that is responding to 4 pulses. So you can see 1, 2, 3, 4. There was no pulse in here. So it shows good performance characteristics. And what I'll do is I'll show you its response time to a benchmark molecule. This benchmark molecule is rhodamine. It's a standard test molecule that is used to actually calibrate the system. So this is rhodamine B and rhodamine 6G. And you can see that the response characteristic that is determined from the lifetime of the decay is in the order of a few nanoseconds. And we compare very well to what we can expect from bigger systems using these bigger photomultiplier tubes. This is showing the spectral response. So here I'm looking at a shift in wavelength. So this is the light, the excitation source, and this is the Raman signature for those rhodamine dyes, 2 rhodamine dyes. And what I'm going to do is I'm just going to zoom in this part here, because this part here is the part that is related to the Raman signature. And what I'm doing is I'm changing the detection window from 250 picoseconds to 3 nanoseconds. And what you can see, as shown here, is that the peaks remain exactly the same, which means that we are doing a correct Raman identification of these 2 dyes, rhodamine 6G and rhodamine B. Right? So far, I've shown you how we can design a single photon device. I've showed you how we can design a very fast device that is a single photon device. And I've shown you how we can design a small, compact grating that also does focusing so that we can do spectral separation and we can identify chemical signatures or biochemical signatures depending on whether we are looking at a biomedical application or an environmental applications. So we have all the components except the light source, and I myself don't work on light sources. Some of my other colleagues work on light sources. So we can start putting these different components to create more complex systems. And what I'll do is I'll walk you through one such system. I don't think there's time to walk you through all of them. Right? So I'll walk you through functional PET and FLIM. FLIM stands for fluorescence lifetime imaging. So these are 2 common techniques that are used in the biomedical area. Functional PET, PET stands for positron emission tomography, is a kind of tomography that allows you to actually look at the function of the molecules that you're imaging. And from the function of the molecule, you can make identification of the molecule being a good molecule. This means a normal molecule, a healthy molecule in the tissue, or a diseased molecule. And depending on the system you design, you can also give some information about the state of the disease. Is it the early state, the medium state, or the late state of disease? Fluorescence lifetime imaging is exploiting the autofluorescence signature we get back from natural biological tissues. And from the signatures, we extract lifetimes. It could be a single exponential decay or a multi-exponential decay. And from those lifetimes, we could identify the type of molecules we're probing. So this allows us to look at the function of the molecules and the type of molecules we're probing for biomedical applications. So one of the things we're interested in is to make a better positron emission tomography system. Existing positron emission tomography system just gives you information along a line of response. Right? It just tells you that there's an event that has occurred here, and that event is detected by two detectors, so a detector on the left and a detector on the right. And the reason it doesn't give you much information, so it cannot tell you what is this delta x relative to the center of the image that is shown here, is because the response of those detectors are not fast enough. So what we need to do is we need to have fast detectors, and we need to have fast electronics to go along with such fast detectors. So we can determine what is this delta x. And if we determine what is this delta x, then we can improve the signal to noise ratio, and rather than have a response that is like this, saying that yes, there was an event that is along this line, we can say in more detail that the event actually was at this region, and the width of this response is related to the speed of response of the detector and the electronics that we have. So we can do accurate localization. And the more accurate we can localize this, it means that the smaller the spatial resolution we can have, and the smaller the spatial resolution, it means that the smaller the size of tumors, for example, that you can detect. And the size of the tumor is related to the ability of the doctors to actually do preventative measures and to enable you to have a full recovery. So if you can capture those tumors when they're in their early stages, which means that they're really tiny, the chances of a full recovery is very high. If you capture it in the later stages, which means that the tumor is relatively big, the chances of a full recovery decreases very quickly. And the bigger the size, the more dramatic is the reduction in the chances for a full recovery. So the idea here is to try to capture these diseased tissues when they're just beginning, so in the early stages of their birth. So how do we do that? So again, we start out with our input pulse. This is the laser, and this is an optical waveform that we get back from the tissue. So this optical waveform could be a single exponential or multi-exponential. So here we have a pulse, and we look at the response. And what we want to do is we want to measure the difference in time between here and here. And the more accurate we can measure this time, the better we would be able to localize the tissue and the spatial characteristics of the tissue. How big is the tissue? And whether it's a diseased tissue or not using fluorescence lifetime imaging. So again, we can say whether the tissue is diseased, and now we can give some information about the size of the tissue. Right? So what do? We do as we said before. So we design these devices that are operating a single photon avalanche device. We design an appropriate threshold, so we can get pulses that correspond to the detection of a single photon. And then if we keep repeating this experiment, we can develop a histogram that will give us the time characteristics of the device. And then if we combine it with the spectral grading we can have the wavelength characteristics of the device. So we have three pieces of information. We have the intensity, so we can get the intensity. We have the lifetime that is related to the decay, and we have the spectral characteristics. And with this three pieces of information, we can accurately identify tissues, and we can accurately identify the state of the tissue. Again, whether it's a diseased tissue or a benign tissue or a healthy tissue. Right? So these are some of the chips that we've designed to do these types of results. So this is the full chip. Right? We've done these measurements. Oh, let's go back. And here you can see that we can go down to 156 picoseconds. So we can do this time stamping between the initiation of the pulse and the response that is around 0.1 nanosecond. And in this way, we can accurately reconstruct the time domain characteristics, and with the single photon characteristics, we can determine the intensity, and with the grating, we can determine the spectral characteristics. And again, with this information, we have most of the information we need to make a correct diagnosis of the tissue. Right, so this is an example of one of the chips that we designed. So this is a different chip from the one I showed you before. This one has around 10 picoseconds timing resolution. It was measured at 400 nanometer. It's very small, so small size is important, and I'll explain this why. It consumes not too much power, and it has a pretty good photon detection efficiency of around 25%. The small size is important because ideally what we would like to do is we would like to put many of these together to create what are called digital silicon photomultiplier, which would be the solid state equivalent in a digital format to the single photomultiplier tube that looked like the big vacuum tube I showed you before. And in this way we can have very complex two-dimensional array of these digital silicon photomultipliers that will allow us to do two-dimensional mapping of tissues. Maybe I'm going to skip this one because I want to explain one other thing to you. Come on. Come on. Okay. So the last thing I wanted to explain to you is how we can create what is called a smart endoscope. So typically, if you have some problem with your gastrointestinal system, so the upper part of your gastrointestinal system, the doctor would insert an endoscope, and all endoscopes that are being used today by clinicians are white light endoscope. So when the doctor is doing the examination, what he does is he looks for differences in coloration. What is the level of whiteness, or the level of pinkness, or the level of redness of the tissue he's looking at. And based on his experience, he might say, okay, this looks a little bit diseased. And then in the endoscope, there's a small opening. That small opening is what's called a working channel. He would insert something like an alligator clip. And this alligator clip would go inside the working channel, and he would actually pinch a little bit of the tissue, and he would withdraw it. And then he would put that tissue on a glass slide, and he would send it to a pathologist or a clinical microbiologist to make an identification. Sometimes they actually stain the area if they think it's a disease area or a cancerous area, or they might even staple it. But your body is very good. If you put some foreign object, such as a stain or a staple in your body, eventually it will reject it. So depending on how long he waits before he comes back to do the second investigation, depending on what the pathologist tells him, he has a hard time identifying exactly where the spot was. Usually he makes a little drawing and he puts an X in that drawing. So he would make a drawing of your stomach or the upper part of your small intestine or your esophagus, and he would say, okay, this is where I took the tissue from. But your stomach is not stationary. It's not like your heart or your lungs or your kidney. It actually moves around a lot in your body. So when he comes back, he has a very hard time doing the identification of where he did the initial probing. So what we want to do is we want to use these high-performance imagers with spectral separation characteristics to design an on-the-spot probe so that we could say whether the tissue is diseased or not. So how do we do that? So again, we look at the time response characteristics, we look at the spectral characteristics, and we put them together to create these three-dimensional maps. So this is intensity versus time versus wavelength. And what the clinician would need to do is he would need to have a database in which different types of tissues in different states of disease, ranging from healthy to very diseased, has already been calibrated and has stored in the database their three-dimensional maps. So these would be like different shapes of mountains. And when he now inserts the endoscope with this additional probe that allows him to reconstruct in real time these three-dimensional maps, he can do template matching. And depending on the result of this template matching, he can say on the spot whether the tissue he's looking at is diseased or not. And he can also state whether it's in the early stages of the disease or the later stages of the disease. So this is one of the probes we're working on using some of the components I showed you earlier. And this would be in the working channel of the endoscope so that we could do this real-time identification. Okay, so what I've told you so far in the second part of the talk is that we can create these ultra-high-speed imagers by separating out the image acquisition from the transfer of the image, but then it suffers from the fact that it's not sensitive enough. To make it sensitive, we can create a solid-state equivalent of the photomultiplier tube that is called a single photon avalanche device, right? We can have it with passive quenching, we can have it with active quenching, and we can use clever circuit techniques to actually reduce the response time so that we could reset it very quickly and have sub-nanosecond response that will allow us to capture these autofluorescent signatures from natural tissues. I've shown you a few examples of these high-performance imagers that are built using single-photon avalanche devices, time-gated single-photon avalanche devices. I've shown you a little bit about time-correlated single-photon counting, where we can actually do these timestamps to determine better spatial resolution in positron emission tomography, and we can create digital silicon photomultiplier tube by making them very small and combining many of them together in one digital pixel. So with these tools, clinicians and environmental scientists can see better. They can see down to single photons, and they can see over a larger range of wavelengths, and they're no longer limited to just visible white light imaging. Now, all of these systems that I told you have one big challenge. The big challenge is, how are we going to integrate all these different components? We have to integrate the light sources with the passive optical components, with the active optical components, and with the imager array in a very small form factor, especially if we're going to use it for in vivo probing to identify the state of tissues. Today there's no time, otherwise I will tell you how we can use such a system for what is called brain tumor margins to determine when the tumor ends and the good part of the brain begins. But you can think about it. We can apply the same technology to actually do this. And the idea in the long run is to create what is called a smart scalpel, so that when the neurosurgeon is actually doing the surgery, he will know when the bad tissue finishes and the good tissue begins, so he doesn't cut out too much of your brain or too little. Because in both cases you suffer. If it's too little, he has to come back and do the surgery again. And if he's doing it again, most likely he will take out a little bit more than he should. Sorry. So this is my last slide. So, thank you very much.
Thank you, Jamal. So a very interesting talk. I think we do have time for some questions. So any questions? Evelyn?
Could you tell us a little bit more about the trade-offs for your CMOS single photon imager in terms of what's the pixel size, what is the wavelength separation you have, and you showed us your images for rhodomine. What if you have a sample with multiple molecules that you want to image, because you're using something where you want to be sensitive to single photons, but you're avalanching it, so your sensitivity to noise is not just thermal noise, but it's random light. What are the trade-offs here, and what limits your reset time? Is the capacitance of the junctions? How small can you get it?
Okay, so you asked several things. So to get around the noise issue, so for example, to get around the dark noise, one of the ways you can do is you can design an array of single photon device. And you can use statistical techniques, and by these statistical techniques you can say, yes, it is a photon, and yes, it is a false event. So there are techniques for getting around that. In terms of the dead time, so the active quenching and reset, you're limited by several things. You're limited by the capacitance of the diode itself, you're limited by the passive resistor, and you're limited by the circuitry and the speed of response of those circuitry. We've designed circuits that have sub-nanosecond response, and these sub-nanosecond response are good enough for most autofluorescence that you get from natural biological tissues. I didn't show here, but we've actually done probing of rail tissues inside the stomach, and different parts of the stomach. And we can make an identification between the type of tissues, for example, whether it's closer to the esophagus, whether it's in the beginning part of the stomach, the middle part of the stomach, the bottom part of the stomach, and the beginning of the colon. Those measurements were done using our photodetectors, but only the photodetectors were used. The optical components were big optical components. So it was a benchtop type instrument with new types of photodetectors that replaced the photomultiplier tube. So those are the sorts of things we've done already. The pixel size depends on whether you want to design single pixel or you want to design an array. So typically these would be 10 by 10 microns or a few tens by a few tens of microns.
You much along the same lines. Could you go to your Raman slide? I think it was 29.
This is 29?
Well, the one where you showed your Raman set.
Okay.
Yes.
This one?
Yes.
Okay.
So here you're counting where you say photon counting. You have a single detector.
In the example, so in the results that I showed you, so these results here, here and here. So this was a single detector that was moved along the... You mean here?
Yes.
Yeah.
So you've got the Raman shift comes from the dispersion you have with a concave mirror.
Concave grading.
Grading, okay.
So it's spectral separation and focusing.
Yeah, I don't quite understand, because I'm colorblind, what these different
okay.
are.
Okay.
It looks as if you're deconvoluting data that you have. Is that correct?
That's correct. So this specific die...
So what information have you additionally used that provides the evidence that you should deconvolute? One of the big problems of Raman spectroscopy is to know which signals you have, and to some extent you've chosen your object so you know where the peaks are and how to deconvolute.
Absolutely.
So if I gave you a mystery material with peaks in the same area, what would you do?
If it's a mystery, so first, these different peaks are for different windows, right? So the position of the peak should not shift with the window. So that's what I'm demonstrating here, right? With the symbols, what I've done is I've deconvolved it using multiple fits, and in this case, only 2 fits are good enough to have a good reconstruction of the raw spectra that we get. The spectral, okay, so the spectral separation of the grating we designed, so this was a grating that was, I think a few millimeters by a few millimeters by less than 1 millimeter. So it's a really tiny grating, was around 1 to 2 nanometers, which is more than good enough to do this separation. This system that we were designing is a system for chemical identification of pollutants in water. So for that,
you see, if you use a standard Raman system, you don't need this high speed. Standard Raman systems don't even have PMTs nowadays; they just have CCDs. But you obviously got information here that relates to the speed of detection that's missing in normal Raman spectra. So I'm just wondering what that is.
Okay. So what I want to do is to show you how we can create the individual components that we can then put together for new applications. So you're absolutely right. For a normal Raman spectra, we don't need speed. What I'm doing is I'm taking some of the components I've designed for Raman spectroscopy and using it for autofluorescence imaging.
Is this particular chemical you're looking at, is this showing autofluorescence? Or
No. Sorry. Yeah, this one has a fluorescent signature. So that's is it the previous slide? Yeah, here. It has a fluorescent signature. It has a Raman signature and it also fluoresces. This dye, this specific dye. No. Yeah. No. So, okay, you're missing one point. So let's come back here. Okay. What I want to do is to show you using those same components I've used for Raman spectroscopy, but for a biomedical application. In the biomedical application, I need to know what is the lifetime, I need to know what are the spectral characteristics, and I need to know what are the intensity.
But if those are true Raman signals, there would be no time dependence.
No.
That's right.
Yeah.
So,
Yeah. But it's 2 different applications, so don't get it mixed up.
I understand now.
Okay.
But I've missed that in the way you described it. I'm afraid.
No, what I told you was that I will use those components now for biomedical applications. Yes?
Thank you, Raman. You talked about the system integration of the silicon images. So could you explain more about what kind of system integration you are going to do and what is the backlight, not backlight, the lighting source of the silicon images you need?
Okay, so depending on the application, we would use different light sources. So typically the autofluorescence signatures are made using UV. So typically from around 350 or 300, let's say, to 400 nanometers, right? So that's one application. So in this case, you would have the light source, you would have all the optical components, you would have the imager, and you would have the electronics. And you probably would have some control electronics also and some synchronization electronics so that they would all work together. And some would be made using silicon technology and some would be made using compound semiconductor technology. The light source, for example, would be compound semiconductor technology. So those need to be integrated on a common platform. It could be a silicon platform or it could be a glass platform. And it would involve standard materials and also new types of materials that we normally don't deal with when we're doing integration. So for example, it may involve some soft materials.
So the lighting source you're talking about, it switch on and off together or you can modulate?
We can modulate it. Yeah. And you had another question?
What kind of system integration you are going to do?
Okay. So one of the system integration technology we're working on is a technique that is called surface activated bonding. I don't know how much you're familiar with this. Okay, so what's the idea here? So if you look at things in nature that connect together, they connect together almost with perfect crystalline going from one system to the next system, but it takes a very, very long period of time. An example would be the oyster, right? So what we want to do is we don't have this long amount of time to wait. So surface activated bonding is a technique where you actually prepare planar surfaces using appropriate chemical treatments so that when you put those two surfaces together, they will want to replicate what nature takes a very long time to do. But this is not easy. This is the most challenging part. But I myself will not spend a lot of time on that. I think this is for an industry to do. What I want to do is I want to demonstrate that the system works and it can actually do what we think it can do.
I just have two questions. The first one is related to your first part, related to very high speed imaging. I'm just wondering how you can get such a high frame rate if you are using an APS, because you'll be limited by the integration time of the pixel. This is my first question, and the second question would be if you are adding polarization light component, would that improve the detection? For example, if you're looking not only at intensity and wavelength, but also polarization angle of the light. Okay, so improve the detection.
So to answer the second one, I haven't considered polarization. Why? Because I wanted to go the simplest way first. To answer the first question, when I explained about the high-speed APS, what I explained is that it's not sensitive to low light levels. So we can just what we have demonstrated is that we can use, under appropriate light condition, an APS that has been modified for high-speed applications. But for the photon-starved applications that we're going after, we don't use the APS structure at all.
But do you have a reset signal using the APS? So do you reset and then wait for a certain time for integration? Or?
No. This would be capturing 8 frames one after the other very quickly. And then it would be reset after 20,000 frames per second.
It's continuous time, it's not integration-based APS.
That's right.
In your talk, you mentioned that your system probably can see the smaller tumor size, right? But how small can it see?
Okay. So the conventional system, most of them are around 1 centimeter. Some research ones are a little bit less than 1 centimeter. What we're hoping to go down to is probably 1 millimeter. Yeah, so 1 millimeter is very tiny. So for example, for breast cancer, most of the time when they catch it, it's several centimeters. So today there's no time to explain to you. We also have a project on breast cancer.
So with you, now you try to look at all these kind of fluorescent and other kind of optics related thing for the tumor. I don't know if possible you can see those study how tumor form. People study this kind of EMT, MET transition, right? How, I don't know.
No, I'm not an expert in that, but I collaborate with people who are experts in that.
I don't know, but it's something interesting to explore the new application of your idea. Yeah.
As I told you, I'm not an expert in that, but some of my collaborators are.
Can I ask one more question? Yeah. I think in one of the chips you shown, I have seen arbitration separate. Are you using time domain and you need to arbitrate between pulses?
No, this is for the time-correlated single photon counting system.
Can you look at the slide?
Which one?
41, I think.
41?
Yeah, you have an arbiter array. So what does that mean?
This arbiter array is for synchronization between the slow gated ring oscillator and the fast gate ring oscillator, so we can do sub-gate delays.
And then you do that in time domain?
Yes, time domain.
So my following question is about the 45 slide. Could you please
45?
45, yeah.
Oh,
just the
very
last
good.
one. About the tissue.
Okay.
Okay, so use your device, we can make a judgment on the tumor tissue or not. But sometimes the tumor tissue is not only by the morphological change. Maybe some smaller molecular. Could you have some method to make a contact, to make a detection? Or, I mean.
Okay, I didn't get your question.
What I mean is, only your technique is just based on the detection of the tumor cell on the morphological change, right?
When you say, what do you mean by morphological change? You mean a physical, the structural change?
Yeah, the structure, or maybe you can understand. Maybe you can understand like that. But sometimes the tumor cell, the morphological of the tumor cell is not has no difference with the normal cell, but just their gene expression has some problem. So what do you concern about this in your application?
That I don't know.
Okay, because what I mean is
I don't fully understand what you're asking, so I have to study it. Then I can give you a good response.
Okay, so I think most of our lots of questions, and so thank you, Jamal, for a very interesting talk. So the good news is Jamal was here for another 6 weeks, I believe. So if you have time and you still want to ask questions, Jamal will be in his office in both IAS and the ECE department, depending on where he is. So thank you, and thank you, Jamal.